This conference will now be recorded.
Hello everyone. So this is the first class for this chapter, which is some basic concepts of chemistry. So this is, as the name suggests, this chapter is all about very basic ideas about the subject chemistry. So first you have to know what are the importance of chemistry. It is that branch of science, because when we say science, basically in general science, if we consider, there is physics, chemistry, math, right? So among these three, it is that branch of science which deals with composition, structure and properties of matter. So if we know this chemistry, then we can say that for any particular object, we can now predict its composition, its structure, and what are the properties. Now, chemistry has a direct impact on our life and has wide range of applications, as you can see in the right hand side pictures, in different fields. Now, basic things if we consider for day-to-day living, that is food for eating, clothes to wear, and places to live. So these are the basic requirements, fine. So not just these three, chemistry plays a major role also in the other human life fields, right? So not just these three basic needs of human life, but also to improve quality of life in some other aspects, fine. So it is important for us as it is playing some role in our day-to-day life, both in vivo and in vitro. That is, there is some reactions going on inside any living organism we consider, and also there is outside. So chemistry is present in vivo, that is inside any living organism, or outside, which is in vitro. So from both this point of view, it is important us to understand the basic principles of chemistry so that we can address this contribution to a large extent. That is, if we know these basic things, then only we can improve further research, and which will help in the development and growth of a nation. Okay, so these are the importance of this subject. Now once we know what is chemistry in general science, this is one of the subject. There are different branches because chemistry deal with a lot of that is, you can find its application in a lot of fields. That means if there is some branches, that is, if we make some categories, obviously it will be more systematic when we will study chemistry. So that is why under chemistry, which is the general term, there may be these four broad categories: inorganic chemistry, organic chemistry, physical chemistry, analytical chemistry. Though these three we mainly deal with, but the last one is also important for analysis purpose. So first focus on inorganic chemistry. So inorganic chemistry, here you can see the sodium chloride crystal structure, that is a common table salt. So this branch of chemistry, it will, in this branch we will study basically their elements and their compounds which is other than carbon. So you will not find the element carbon or its compounds much in this branch. And when it is organic, it is actually the reverse. Now in organic chemistry, as the name suggests, the compounds that we deal with, it is mostly produced by living organism, and that is mostly carbon and its compounds. You can find many hydrocarbon, that means which is composed of two elements, carbon and hydrogen, and obviously its derivatives. So organic chemistry is concerned with the organic compounds, and organic compounds means it is carbon compounds. So in inorganic chemistry, we will study elements and other compounds, and elements and their compounds, but other than carbon. But when it is organic chemistry, it is basically carbon compounds mainly. So this is the difference between inorganic chemistry and organic chemistry. Now what about physical chemistry? So physical chemistry, you can find some similarity with physics, because in physics what we do, we study some basic fundamental principles, fine. So that is why numerical problems like this, that is very common in physical chemistry, because that is all about principles. And here we have picture of organic chemistry. Then what about analytical chemistry? It is that branch of chemistry. If we study this, what we can do, it will help us to analyze different substance in qualitative and quantitative way. Now when I'm saying qualitative and quantitative, it means suppose we have any unknown sample and if you want to know any particular compound is present or not, you have to do some test, which is basically qualitative test. And after doing this test, the results that you are getting, from these results you can understand whether that particular compound is present or not. So this is qualitative analysis. We are not doing anything regarding how much amount it is present, what is its weight, that we are not dealing with. But when it is quantitative, you already know which in the sample what is actually present, but you do not know what is its quantity. So suppose some particular compound is present, suppose calcium is present, but you do not know what is the amount of calcium. In that case, we do quantitative analysis just for the to find out this unknown amount. We know what compound is present, but we do not know what is the amount. So that is the difference between qualitative and quantitative analysis. This is mainly based on calculation. There is many calculations you can find in analytical chemistry, and also different types of instruments are also used. We should know what are their principles of this instrument. There is a principles based on which these instruments are operating. Fine. And so these four here it is mentioned, but that is not the end of the branches of chemistry. If we consider, there are other branches also. So in addition to this, some few are mentioned. Don't think this is the end, but still we will see only some names. Biochemistry, so all the chemical reactions that are going on in vivo inside our body, living organism. Biochemistry is all about that. Okay, then so that is why it is biochemistry. Biology, as if it is combination of biology and chemistry. Then nuclear chemistry, as the name suggests, nucleus. We know when we consider atom, so this is if it is the nucleus, outside there are electrons surrounding it, it is revolving. But when we consider chemical reactions, basically it is involvement of only the electrons that are moving, that is surrounding this nucleus. So that is about chemical reaction. But when I am saying nuclear reaction, that means now the nucleus which is present in the center of the atom, that will take place in reaction. There will be some change in the nucleus, and nucleus is composed of proton and neutron. So proton, neutron, now it will take part. But when it is normal chemical reaction, only the electrons that are taking part. So that is why it is different. So nuclear chemistry, it is involving mainly the reactions that are related to nucleus. That is why the name nuclear chemistry. Then forensic chemistry, art chemistry, etc. These are other branches. Fine. So here we have some basic idea about the branches of chemistry. Classification of matter. So in lower grade 9 or 10, you already know what is matter. That is a basic definition we know. But here we will elaborate it. That is how we can classify this matter and also related examples. So the first classification that we are doing, matter, you can have classification whether it is that is chemical or physical. Fine. So when it is physical, it is actually very easy to understand, and you will not find much variation. That is subdivision, it is not very high. Solid, liquid, gas. That means what is the outer appearance of the substance that you are dealing with. If it is solid, that means, for example, if you consider water as substance, water can remain in solid form, in liquid form, or in gaseous form. But actual substance is water, that is not changing. Only the outer appearance is changing. Water is basically having formula H2O, that means 2 hydrogen atoms, 1 oxygen. So this is formula. So formula will remain same whether you consider ice, solid form, whether you consider the liquid form, and whether you consider the gaseous form, that is the water vapor, steam. So in all these cases, chemical formula is same. It is H2O, whether it is solid, liquid, or gas. That means in chemical composition there is no difference, only the outer appearance is different. So based on this, we can have this classification. Now come to this side, chemical. Now there will be some change in the chemical bond also. Under this we have pure substance and impure substance. Now mostly we do not use the term impure, we say it is mixture. And pure substance, again classification, subdivision is there. For mixture also there is subdivision. So physical state of matter can be converted into one another if you change temperature or pressure accordingly. Okay, so from ice, which is the solid form, if you increase temperature you will get water, then further increase in temperature you will get vapor. Similarly, if you move in the reverse direction from vapor to water to ice, you have to decrease the temperature. Okay, so what is mixture? Mixture is consist of more than one chemical entity present, but these entities, they are not reacting with each other. So suppose I am writing here A plus B, or another sample of mixture, suppose A plus B plus C. So in these cases you have two chemical entity A and B. In the second case you have three chemical entity, which is A, B and C. So this A, B, C or A, B in the first case, they are not reacting with each other, they are remain as it is. That means their individual chemical properties are not changed, but they are together. So that is why it is mixture. They are not pure in pure form. Okay, and they can be further classified based on their physical appearance, which we will see. But what about pure substance? Pure substance, there is only a particular element present. So when I'm saying element, suppose if you just consider the periodic table, all the elements are present. So when it is pure substance, there will be a single element. We cannot have, sorry, what I'm saying, there will be composed of simple atoms or molecules, but there will be only one entity. Now under this pure substance also subdivision is possible. So what is this subdivision? First see the subdivision for pure substance, then we will go to mixture subdivision. Element and compound. So when it is element, as the name suggests, it is a single element. Fine, but not necessary. It will be always single element. Suppose 2 to 3 elements together, it is making some compound by chemical reaction, then you will get compound. But it is also pure. It is a particular entity. So in case of mixture, when I have said A is an entity, B is an entity, and they are not reacting with each other, right? So just like that, when it is compound, but still it is pure. Here we have example, copper sulfate. So the formula is CuSO4. So in this case, how many elements are present? We have three elements. We have copper, we have sulfur, and we have oxygen. So three elements are present. But if you look at the element option, examples are given: metal, example copper; non-metal, sulfur; metalloid, silicon. So three individual elements are present. Just remember periodic table. In periodic table, copper is present in the D block in the middle part. Then non-metal sulfur, it is present in the P block. Non-metal sulfur. There are so many other types of non-metal. Only sulfur is mentioned here. Similarly, metal, copper, there are other types of metals. Some metals you can also find in S block. And silicon, metalloid. Now metalloid means having property which is in between of metal and non-metal, not exactly, you can have intermediate property. So that is why it is metalloid, but they are individual element. This is copper, sulfur, this is silicon. Okay, so these are the chemical symbol we use for these three elements. Now in case of compound, there must be at least two elements. In this particular example, copper sulfate, we have three elements: copper, sulfur, oxygen. So when it is copper sulfate, which is formed from these three elements, and there is some particular bond present between copper and sulfur, sulfur and oxygen. So individually, you will not find the properties of copper, pure sulfur or pure oxygen, because now these three elements together, there is some chemical bond between them. they have formed this compound. So individual properties of copper, sulfur and oxygen, it is no longer present. So now they have formed a completely new compound, which is copper sulfate. But copper sulfate in itself, it is pure compound. So pure substance may be two types. Element, only one element, where only one element is present. And compound, where two or more than two. In this case, you can see it is three. They are chemically combined and they have formed something completely new. They are individual properties of these original elements, they are no longer present. So that is difference between element and compound. Now come to this side, mixture. Here we can have two more subdivision, homogeneous, heterogeneous. Homogeneous, we have example green tea, and this is oil and water. So if you consider green tea, here it appears as if it is just a pale yellow color and transparent liquid. So it seems as if there is no layer separation, right? But when it is heterogeneous, example oil and water. If you take oil and water together and shake vigorously, keep it for some time, gradually there will be layer separation. So this is the layer of oil, this is the layer of water. So they do not mix with each other. And you can, in this case, you can see this layer. So easily from that is just by looking at it, you can understand there is two different phase present. It is not single phase. So that is why it is heterogeneous. But when it is single phase, it appears as if it is pure, but obviously it is not pure. There is so many entities present, but because of its appearance, it appears as if it is single phase. So that is why it is under homogeneous. So that is all about classification of matter. So as we have seen, element and compound, which is under pure, remember, pure substance category, we have seen element and compound. Now we will go into the details. An element consists of only one type of atom. Okay, only a single element. Now we know that atom is the smallest electrically neutral particle. Electrically neutral. So there is no positive charge, no negative charge. But atom, it consists of fundamental particles, electron, proton and neutron. Among these three, electron is negative, proton is positive, neutron, it is neutral. Okay, so atom is consisting of electrons, protons and neutrons, but as a whole atom is electrically neutral because of the same amount of positive and negative charge. So there will be a particular atom. So two different atoms, not possible. It is possible that atom of same element is present more than one. That is fine. But two different elements will never be present. So element can be monoatomic. For example of monoatomic is gold, copper that you have already seen, then sodium. Okay, but when it is polyatomic, single element but two atoms together. So hydrogen, it is diatomic because two hydrogen atoms, they are combining together and now they are making H2. This is diatomic. Similarly, the element phosphorus, if you look at its chemical symbol P4, that means total 4 phosphorus atoms. It is not that one phosphorus atom then atom of another element. No, all the atoms are of only the element phosphorus. It is tetraatomic. Then sulfur, octatomic, because 8 sulfur atoms present together. So you can use the term molecule only when there is more than one atom. If it is 2 diatomic, triatomic, tetraatomic, and when it is in general you can say it is polyatomic, then only it will be molecule. But when it is single atom present like sodium, potassium, you see it is not Au2 or Au3, it is a single, only one Au, only one Cu. So that is why it is monoatomic. Then what about compound? Compounds are made of molecules which contain two or more atoms. So at least two different elements must be present, because if it is all the two atoms, they are of same element, it is no longer compound. So in compound there has to be at least two different elements. It may be more than that. So the properties of a compound are altogether different from the constituent elements. Look at these examples. Carbon dioxide. So what are the elements present? Here we have the element carbon and we have the element oxygen. The first element only one atom, the second element two atoms. Now when we are saying it is carbon dioxide, individual property of carbon and oxygen are no longer present. Fine. Similarly, if you consider glucose, total three elements are present: carbon, hydrogen, oxygen. 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. But individual properties of carbon, hydrogen, oxygen, that is not present. Okay. Hydrogen sulfide, H2S. Two different elements present. Hydrogen, its two atoms are present. The second element is sulfur, only one atom is present. Okay. So in compound, you can see at least two elements must be present, but in element it is always a single element. Atom number may vary. Depending on that, under element, we have seen polyatomic and monoatomic. Another polyatomic example, suppose very common oxygen, very common nitrogen, right? But when just look at these two, individual nitrogen and oxygen, these two elements when combined together, we can have different types of compound. Just one example I'm giving, NO2. So in this compound, you have two elements, nitrogen and oxygen, but individual properties of nitrogen gas, oxygen gas are no longer present. Similarly, another oxide of nitrogen, NO or N2O4. In all these compounds, two elements are present, nitrogen, oxygen, but their chemical composition is different, so the compounds are also different. Fine. Let's discuss this problem, which is based on this classification of matter. By applying the knowledge of chemical classification that we have just discussed, classify each of the following substances into elements, compounds, or mixture. Sugar. Okay. So in sugar, mainly glucose is present, and the formula it is, you can consider as if this one. So here you have three different elements: carbon, hydrogen, oxygen. So obviously it will be a compound. Then seawater. So in seawater we know table salt is present. Now table salt is sodium chloride. So there is sodium chloride and there is water. But individual properties of water and sodium chloride, it is still present. So that is why we cannot say that is NaCl is not reacting with water. They are just together. Fine. So it is a mixture. Then distilled water, carbon dioxide, copper bar, table salt, which is also present in seawater. But when table salt is simple table salt that we use in kitchen, that is basically only sodium chloride. So this will be compound. Fine. Then silver plate, it is made of silver only. Naphthalene balls, there is presence of carbon and hydrogen, it is basically hydrocarbon. So two elements are present, right? Copper wire, it is only copper, only one element is present. That means it will be under element category. So now the result is under element you can have copper wire, silver plate, but for that is only one mixture is present, which is seawater, because it is mixture of NaCl, that is table salt and water, and the rest of the substances they are compound. Okay, so that is the answer. Mixture and its types. So now we will elaborate the discussion of mixture, because under this mixture category we have seen that there is two types: homogeneous and heterogeneous. The combination of two or more elements or compounds. Two or more elements, if we take any example, if you consider air, in air there are different types of gases present. So all these are together present, but they are not reacting with each other. So you can say as if it is, that is, if you consider only oxygen and nitrogen, because they are individual element, oxygen as element, nitrogen as element, and they are present as diatomic gas in air. So if you consider air as a mixture of O2 and N2, it is mixture of two elements. So it may be combination of two or more elements, or it may be mixture of compounds also. So it may be two compound, it may be one compound, one element. Okay, but remember the condition that must be fulfilled, they are not chemically reacting with each other. So individual chemical properties should be still present. Okay, so they are not chemically combined together and are present in any proportion. So when there is a mixture, and this that is two or more elements or two or more compounds are present, they are present in any proportion. Now types of mixture, as we have seen, homogeneous. So for homogeneous, this picture, if you see carefully from this picture, if you take any part from wherever is the position, you will always find same composition. So there will be two purple balls and two green balls. That means it has uniform composition throughout, and you cannot find any phase. So visible boundaries or separation, layer separation, these type of things you will not find. And whatever is the, that is from any part, suppose you have coffee, you are taking any part from any part, it will always have uniform composition, right? So these are some examples that you are seeing here: natural gas, steel, vinegar, coffee. Natural gas is mixture of two gases basically, air also, that we have just discussed a few minutes ago, wine. So all these are homogeneous, you cannot find any layer separation type of thing, and it is always having uniform composition. But when it is heterogeneous, mostly the things that we see surrounding us in day-to-day life, they are mostly heterogeneous. Okay, so a mixture is said to be heterogeneous if it doesn't have uniform composition. So that is the main difference between these two. Here uniform composition not present, but in homogeneous uniform composition is present. And that is also clear from this picture of these two colored balls. So if you take any part from this, you are getting only the purple entity. If you are taking in, you are getting mostly purple, sorry, mostly green, only one. If you are focusing on this, you are getting only green. Fine. That means uniform composition not present throughout. And you can also find some visible boundaries. So it is not looking homogeneous, just like if you just compare this the previous picture, when we consider air or vinegar, it appears as if it is a pure compound, though it is not, but it appears as so. But here you can already find the boundaries, the different constituents of a heterogeneous mixture. You can easily see even with naked eye. Okay, so remember the oil and water, that example we have seen 2 to 3 slides before. You can easily identify that oil and water is present. But homogeneous, it appears as if it is pure, but it is not so. Inorganic compounds and organic compounds. Inorganic compounds mostly will deal with non-carbon compounds, or better we say the compounds which are obtained from non-living sources, rocks, minerals. These are in fact the compounds of all the elements except hydride of carbon, because whenever it is hydrides of carbon or their derivative, that means you can also say carbon, hydrocarbon, that is the common term we use. Hydrocarbon means in those compounds you will have only two elements, carbon and hydrogen, and their derivatives. For example, if I say ethane, C2H6, here you have only carbon and hydrogen, right? Now one hydrogen may be replaced by chlorine. In that case, it will be C2H5Cl. So it is chlorine, chloro derivative of ethane, right? So it is either hydrocarbon or their derivative. Those compounds are basically organic compounds. But in this case, Except carbon, you can find all the other elements. So under inorganic, we have example salt. If you consider table salt, not just table salt, any salt you can consider inorganic compounds. For example, KCl or calcium chloride. So these are also salt. And diamond, which is carbon present, okay, and carbon dioxide, that means CO2 gas. So it is not that carbon will not be present, it is not like that. Don't think it is, that is, don't be confused with the definition. I'm not saying that when it is inorganic, carbon cannot be present. No, that is not the thing. But it is not carbon hydrogen compound made. But when it is organic compound, you will see mostly it is carbon hydrogen. So examples, if you see methane, the formula is CH4. Benzene, the formula is C6H6. Then we have carbohydrate, protein, oil, fats. So protein, fats, all carbohydrate, all these you can find in living sources. They are not non-living sources. Okay. So these are the compounds which are derived from living sources in plants as well as animals, and they are mostly hydrocarbons and their derivatives. Physical properties and chemical properties. Physical properties can be measured or observed without changing the identity. That means chemical composition is not changed when we are observing or measuring these properties. Here we have example: color, odor, melting point, boiling point. So a particular compound, when it is melted, just take ice. It is a solid form of water. When it is melting, temperature 0 degrees centigrade. So we can say that the melting point of water, it is 0 degree. But now after that is, once it is reaching 0 or lower than that, it is converted to solid. But that doesn't mean the chemical composition of liquid water. Chemical composition is, it is having formula H2. So that formula is still present, whether you take it as a solid form or vapor form. So chemical composition is not changed. Similarly, when it will reach 100 degrees centigrade or more than that, it will be converted to vapor. So this melting point, boiling point, these are basically physical properties. Then color, odor, it has nothing to do with the chemical composition. It is completely independent of that. But when it is chemical properties, these properties require a chemical change. So there must be change in the bond for formed between two atoms. Examples are acidity, basicity, combustibility. So if you want to know a particular compound, so acid, just take simple hydrochloric acid. So if you want to know its acidity, that is, if you want to know the property acidity of this molecule, you have to do some chemical reaction. So you need some basic reagent with which it can show its acidic property. So there must be some bond breaking. The bond between hydrogen and chlorine will be broken. Similarly, if you want to check basicity of any compound, suppose potassium hydroxide, you want to check its basicity. Obviously, it has to be involved in some chemical reaction. Then combustibility, that is reaction with oxygen. Mostly combustion reaction, it is examples, if you see, we'll see it is hydrocarbon compounds. They are reacting with oxygen, such as methane or ethylene. They are reacting with oxygen and they are producing carbon dioxide and water. So that is combustion reaction, which is reaction with oxygen. So that means here also bond breaking, bond making, all these things are involved. So that is the difference between physical and chemical properties. Physical quantities and their measurement. Now, if we want to express different physical quantity, for example, I am mentioning temperature of any particular compound. So when I am saying it is, suppose I am saying it is 500, but it doesn't make any sense unless you are using any unit. So once you are saying that it is 500 degrees centigrade, so this is the unit, now it makes sense, right? So you need not just the numerical value. 500 is the numerical value, but mere saying that the temperature is 500, it doesn't make sense. You have to mention the unit. You can also say that it is 500 Kelvin, which is another unit of temperature. So here we need, when we are expressing this or measuring this physical quantity, we need two things, the unit and the numerical value. So here the 500, this is the numerical value, but without unit it will have no meaning. So unit is also required. And similarly, if you simply say unit, that is also not making any sense. You need both of them. Now when it is unit, it can be two types. It may be fundamental unit or it may be derived unit. So from the name itself, you can understand the difference. Fundamental means there will be use of only one unit, but when it is derived, you will see there will be at least two units together, and they two together or more than two combined together, and they are making a new unit. So that is why it is derived. So when we'll see example in the next slide, it will be clear. So fundamental unit, or you can say also basic unit, these units which can neither be derived from other units nor they can be further resolved into simpler units. So further resolve, that also we cannot do. So that is why it is fundamental. And under fundamental we have all these examples, very common, these three: length, mass, time. How we measure this? Length you can measure in meter, though there are some other units also, but just focus on this. Here we have taken meter. So in meter there is no other units involved, it is only meter. Symbol we use small m. Then kilogram. For mass we use kg. Then time, second, it may be minute or hour, but when I'm saying second, it is mentioned with the symbol s. Fine. Some other examples are also there. And remember, this system, that is SI system of measurement, though there are other systems, that is CGS also, but this system of measurement, that is the most common system employed throughout the world. So that is why the examples that you are seeing here, or further you will see, that is mostly SI, because if we sometimes use SI, sometimes use CGS, it will be confusing. So here we are focusing mainly on SI system, not CGS. What about derived units? So derived units, they are obtained from some other units, so that is combination. So it depends on the fundamental units, or which can be expressed in terms of the fundamental units. See what examples we have. Suppose we have density. Now density is mass per unit volume. Now when it is mass per unit volume, that is m by v, so mass will have a different fundamental unit, kilogram. Volume will have different fundamental unit. See, it is length, but we know length, when it is 3 times, then it is volume. That means it is cubic meter, that is m to the power 3. So it will be expressed in this way. So basically here you are taking help of two fundamental units. One is kg, another one is meter. Similarly, if you consider simply volume, that is also meter multiplied 3 times. It is cubic meter. So volume is also derived unit. Okay. So here though it is only meter, but as we are taking it 3 times, that is why it is under derived unit category. Then speed, that means distance per unit time. So distance meter is used, and for time second is used. So this is also derived. Then for Newton, see, kg into meter divided by a square. So 3 individual derived fundamental units we are using, but the combined sign we use capital N. Though you can write it this also, but for simplicity we use capital N. Then joule, we express energy unit in joule, capital J, but it is actually kg meter square by per second square. So 3 individual units are present, but we do not write it in this way. We mainly write G. Pressure, Pascal, that is capital P and A. It is kg divided by ms square. So that is the difference between fundamental unit and derived unit. Now sometimes we have to use some prefixes. Prefix means the actual symbol that we use for the different unit. just before it we will use some prefix. Okay, so basic unit, as you can see here, we have, suppose just take, okay, let me show you both these together so it will be helpful. So suppose the basic unit is 1. Okay, now when it is 10 times, then we use deca, or the symbol is da. So these symbols are now used before the actual unit symbol. Then when it is 100 times, it is hecto, h, though hecto, deca, it is not very common, but you know kilo is very common. Now suppose I am saying gram, so it is g, right? But when I am saying kilogram, that means 1000 gram, because 1 kilogram is 1000 gram. But when I am placing k before this small g, now it is kg. So when gram is, which is the basic unit, it is 1000 times, you can write it as kilo. So it is now kilogram. Now here it is mentioned as 10, then 00, then 000, and it is increasing. But if you want to express it in a simple way, it is 10 to the power 0, which is actually 1. Then gradually the power is increasing. So 1000 means 10 to the power 3. 100 means 10 to the power 2, like this. Similarly, if it is not 10 times or 1000 times, suppose it is 10 times less, that is 1 by 10. So now it will be 0.1, or you can say it is 10 to the power minus 1. Suppose it is 100, that is 1 divided by 100. So now it is 0.01, or you can write 10 to the power minus 2. So in this case, the prefix that we use, small d, small c. Suppose I am saying basic unit is meter. But if it is 1/10 of meter, 1/10 of 1 meter, then you will say it is decimeter. So normally meter we express with small m, but when it is 1/10 of meter, it is decimeter. So now you will write dm. Sorry, it is not working. You will write dm. When it is 1 divided by 100, that is 100 times less of actual meter, it will be centimeter. That means cm. Then if it is 1 divided by 1000, it will be millimeter. Then micrometer, nanometer. So gradually it is decreasing. So either it may be increasing if we move up, or it may be decreasing. So when you move down. So these are the prefixes that we use depending on its value is going towards lower side or higher side. Okay. Scientific notation. Scientific notation is a form of representing a few numbers in a simple form. But why it is required? What is its significance? Suppose I'm saying any number, suppose 40 or 4. It is very simple. But if I am saying it is 400, so it is very large number, right? So in this case, rather than writing it in this way, we can write it in a different way. So in day-to-day life, when we do calculation, or you are reading any book, dealing with this large number, or if it is very small number, suppose the number may be like this, 0.0004. So this is very small number. So either it is very large or very small. In both these cases, when you are writing it, it is difficult to handle. So for simplicity, we can represent it in a different way, and that is a scientific notation. So what we do here, we use multiplication form of single digit number, and there is a 10 having a power raised to the power of respective exponent. So how it is represented? It is represented in this way. Capital N multiplied by 10 to the power small n. So here n is the exponent. N may be positive, n may be negative. And this capital N, don't think it can have any value. No, there will be some specific value. So when it is capital N, it should be in this range. It is always lesser than 10, but it may be equal to 1, but not less than 1. So this condition must be fulfilled. So here this 40000, which is basically 40,000 that I have written, you can write it in this way: 4 into 10 to the power 4. Okay, so here capital N is 4, small n is also 4. Similarly, 0.0004, you can express it in this way: 4 into 10 to the power, so it is actually 4 into 10 to the power minus 4. Okay, so why I have written minus? Because now it is, the decimal is 3 digits before 4, so that is why it is 10 to the power minus 4. So in this case, capital N is again 4, but small n is minus 4. So it may be positive, it may be negative, depending on the number is high or low. But remember, capital N always lesser than 10 and greater than equal to 1. That condition must be fulfilled. Exponent is positive, it is very large; negative, if it is very small. So look at this example. Here we have this number very large, 213, then total 6 zeros are there. Now we can write it in this way. So here 2.13 is capital N, right? 2.13 is capital N and 8 is small n. Okay. Now if you are thinking that why the decimal we are bringing it here, we can also write it like this. That is 21.3, and in this case you are moving the decimal 1, 2, 3, then total 6, then 2 more. One more. So it will be 10 to the power 7. But in this case, this is not right. Why? Because capital N value is greater than 10. You have to maintain the condition. It must be lesser than 10 or greater than equal to 1. So that is why this is not correct. This is correct. Similarly, the second one, it is very low value, 0.00872. Now we have to express it in the format of capital N into 10 to the power n, keeping the condition that is fulfilled, which is this one. So that is, it is 8.72. It cannot be 0.872, because if it is 0.872, then it is lesser than 1. If you are writing it as 87.2 or 872, that is also not right. So you have to write it in this way. Okay. Here, just look at this number, which is basically Avogadro number. 6.022, which is capital N. It is also known as coefficient. This is the base and this is power, and also known as exponent. Some more examples if we see. 49, then how many zeros are there? 7. Okay. So we are moving this decimal to this position between 4.9, 4 and 9. You cannot write 49 or 0.49. It has to be in this range that is mentioned here. That is, it is 4.9 into 10 to the power 8, because you have moved the decimal from right to left 8 digit. So that is it, 10 to the power 8. Similarly, the second one, 5.05. So the decimal should be in this point position, and you are moved 7 digit, so 10 to the power 7. Then the next two numbers are very, very low number. Here we will move towards right hand side. So now you are moving towards right hand side between 9 and 7. Then only capital N, its condition will be fulfilled. But we have moved 8 digit towards right hand side. So that is why it is negative. And the next one, the decimal should be here, and we have moved 5, so that is it is -5. Okay. Now we will see some calculations how we can do it using scientific notation. Here we have two terms. First entity, this is second entity. We are multiplying these two entities. In the first entity having power 10 to the power 6, the second one 10 to the power 5. But as it is multiplication, you can directly add the power of 10, which is mathematics, simple mathematics. So you can easily add them, and rest of the two digits directly multiply. You will get 23.94, and 6 plus 5 is 10 to the power 11. You can, if you, the final result, it is not instruction is no such there that you have to mention the final digit in scientific notation. We are just using the scientific notation when doing the calculation. But if you want to express the final answer in scientific notation, then because it is not in already scientific notation, it is 23.94, which is greater than 10. So that is why if you express it like this, suppose 2.394. So now you have moved towards left hand side. So it will be 10 to the power 12. Okay. So you can, another way also you can do it, as I have converted 23.94 to 2.394. That means as if you have divided it by 10, but you cannot do this. You also have to multiply 10. So as if, just focus on this part, it is now becoming 2.394, and 10 to the power 11, one more 10, now it is 10 to the power 12. So I'm just showing you the different ways you can do this, express this scientific notation, but it is up to you which way you want to do it. That depends on your comfort level. So 23.94, you are moving the decimal towards left, so you can simply add 10 extra, so it will be 2.394 10 to the power 12. But another way is as if you are dividing it by 10, so in the numerator also there will be another 10, so ultimately you will get same result. So this is multiplication. Next you can see it is division. So this entity, it is now divided by another entity. Now when it is division, the power of 10 you have to subtract. So 10 to the power 6, it is in numerator, and 10 to the power 3, it is in denominator. So that is, it is 6 minus 3. Suppose if you have 10 to the power 3 in the upper term, that is numerator, and 10 to the power 6 here, then it will be 3 minus 6. But in this case, it is 6 minus 3. And final result is, it is already in scientific notation. Now we will see subtraction. So this entity and the second entity, it is subtracted. Now when it is subtraction, this type of direct power that we have done, addition and subtraction, that we cannot do. So in this case, first we have to make these two exponents same, then only you can take common. So first one we have not changed, but the second one, as this decimal is now moved towards left, so as if you are multiplying 10 to the power minus 4 with another 10, so now it is 10 to the power minus 3, and you can take this 10 to the power minus 3 now common, so it is outside, and rest of the part simply do that subtraction. This is the final answer. Then we have again two entity, power is 10 to the power 3, second entity power is 2. So we have to make the power same, then only you can take common. So now in the first term, this decimal, if you move towards right, so as you are moving right, so the 10 to the power 3 now it will be 10 to the power 2. You can take it common, and you are getting 48.22 10 to the power 2. Okay. Now another way also you can do. Suppose you are not changing the first term, so it is still 4.56. But other term, if you are changing this 2 to 3, now it will be converted to 0.262. Sorry, it is multiplication sign. 0.262 into 10 to the power 3. So now both are 10 to the power 3. So it will be plus 0.262 10 to the power 3 common. So if you do this addition, you will see it will be 4.822 10 to the power 3, which is basically same, because 4.10 to the power 3 is nothing but 4822, and this is also 4822, right? So what you have to do, you just have to make this exponent of 10 common, so that you can keep it outside and calculation will be easier. Okay, and you can change the first exponent or the second according to your that is depending on which one will be easier. Depending on that, you can choose any of them. Okay, so this is calculations. We have seen 4 different examples: subtraction, division, multiplication, addition. On these 4 we have seen. So we will end here. Thank you for listening.